We're going to quickly review how the sizes of ions are also influenced by the factors that dictate Coulomb's law, the charges of the protons and the electrons, and the distance between them. The sizes of ions depend really on three primary factors: the effective nuclear charge of the outer shell electrons, the number of electrons, whether there's increased or decreased repulsion, the orbitals in which the elements reside. Those three factors are going to influence the size of both cations and anions. So cations are positively charged ions, right? They have electrons that have been lost, so everything that's shaded in red is a cation. Cations are typically smaller than their parent atoms. And why is that? Well, anytime we have a cation, we're losing the electrons in the outermost shell. So that's a valid explanation, is to say the electrons that are lost are now causing the outer shell of that new ion to be one energy level below what it should be, because for sodium, for instance, its outer shell electrons are in 3s. We lose the 3s electrons and we're all the way down to 2p. So that's one way to look at it. The other way that you can explain why cations typically get smaller is because there's less total electrons. Less total electrons is going to cause less electron-electron repulsion between the electrons in the ion. Anions are negatively charged, so they have one or two, sometimes three more electrons than the original atom. And the size of an anion is always larger than the original atom. And the reason why that is similar to how we say reduced electron repulsion causes the cation to get smaller. Extra electrons that are next to each other in an atom don't want to be next to each other, right? Because they push against one another. They repel. So that increased repulsion is going to cause the size of an anion to be larger than its original atom. Typically, when we go down a group, ionic size gets bigger, and you can relate that same concept of atomic radius to ionic radius. And the reason why is, well, rubidium has, even though it's a positive ion, it has 4 energy levels of electrons, 1, 2, 3, 4. Extra shielding, those electrons can get further away from the nucleus. So anytime we're comparing ions within a group, yeah, they're getting bigger because they really have more energy levels as you move down a group. We also have this term isoelectronic. Iso means same, the prefix same, like an isosceles triangle has same sides. Atoms are ions that have the same electron configuration despite different effective nuclear charge. So for instance, lithium and beryllium and boron, they all sit within the same period, but these three ions that I have highlighted in red are all isoelectronic, because if lithium loses 1 electron, it has an electron configuration like helium. If beryllium loses 2 electrons, it has an electron configuration like helium, and so does boron 3+. Oxygen 2-, fluorine 1-, both of these ions achieve a neon-like electron configuration by gaining electrons. They are isoelectronic. They have exactly the same electron configurations. So if you have the same number of electrons, we can't really look at the number of energy levels and use that as justification for why the ions are bigger or smaller than other atoms or ions. We just want to look at numbers of protons, because if you have things that have exactly the same numbers of electrons, the tiebreaker would be, okay, well, which one has more protons, which is therefore pulling more on the outer shell electrons. So to arrange magnesium 2+, calcium 2+, and calcium in order of decreasing radius, and then for S2-, S, and O-, I want you to see if you can do that by taking into account two things. Well, number of energy levels seems to have a greater impact on size. And then if two things are isoelectronic, then we need to start looking at number of protons. In this case, though, it doesn't look like we have anything isoelectronic. So see if you can go ahead and put these in order based on increasing atomic or ionic size. Calcium would be the biggest because calcium and calcium 2 plus, right, have more energy levels than magnesium 2 plus. However, calcium has more electrons. Electrons repel each other, which causes calcium to be slightly bigger. And calcium 2 plus, magnesium 2 plus would be the smallest. S2 minus is the largest out of this group because its principal quantum number of its valence electrons is 3. So they're the farthest out. Compared to sulfur, sulfur 2 minus has extra electron-electron repulsion. Okay. Go ahead and see if you can arrange each one of these sets in terms of ionic or atomic size. We might have some electronic species here, isoelectronic species to take into consideration. In the first set, sulfur 2 minus would be my largest. Notice how it says decreasing. You have to be very careful about what the directions are asking you to do. Chlorine 1 minus would be the next smallest, followed by K plus and then Ca2 plus. In this entire list of ions here, rubidium 1 plus would be the largest. All of them are isoelectronic. Rubidium 1 plus has the least amount of effective nuclear charge because it has the least number of protons out of that set, pulling on those electrons, and therefore would be the largest. The next topic that we're going to cover in our next video is going to be how ions are formed, both with ionization energy and electron affinity.